Hi, I'm Tulasi Paradarami, engineering tech lead of the Big Data Group. I have here Marcell, senior software engineer in the Big Data team. We are here to talk about the applications of HBase and Phoenix at 23andMe. 23andMe, a quick introduction, it's a genetic service provided directly to the customers, and that includes a number of reports in ancestry, health, wellness, and traits. So how does it work? You basically order a kit on the website or on the app, provide a sample of your saliva that is shipped to the lab from where DNA is extracted. We analyze the DNA and share the results with the customers. So today, we'll be talking about a couple of use cases for Apache Phoenix at 23andMe, a couple of applications, IBD, identical by descent, and ancestry composition. In addition to that, we'll also be going into some of the technical details of hash joins and the performance improvements that we have introduced to improve the hash joins. I'll also briefly talk about the cluster configuration we use. There are a number of moving parts here. Basically, from the experience of running these clusters the last few years. We'll also talk about the lessons learned from running in production. Finally, we'll sign off with a quick Q&A. So big data at 23andMe. We have over 5 million customers, 1 million genotype locations for every customer. That translates to 5 trillion interesting data points. In addition to that, there are also tens of millions of imputed SNPs. A SNP is nothing but a variation at a particular location on the genome, in simple terms. So we have a few algorithms which compare DNA across the database and save the shared regions in the database. There are over 1 trillion such records that capture the information about the shared segments and the relationships the customers have. In addition to that, we also send across a number of surveys to the customers. The data points collected from those surveys are also stored in the database. There are billions of such data points. About 4 years back, at 23andMe, when we had less than 1 million customers, we started looking at the big data infrastructure, working towards building the next generation data storage system that had few things, that we were targeting few things. Things like performance at scale, support for arbitrary joins and aggregations, and also more importantly, enable internal research by allowing fast random access to any genotypic location across the whole database. During that time, we quickly landed on HBase, mainly for performance reasons, and also its scalability. And using Phoenix on top of it is really a no-brainer, mainly because it provides the SQL interface for accessing HBase. In addition to that, Phoenix has a number of good things that we were interested in. Table sorting, predicate pushdown, joins, server-side aggregations, a number of these things that look very interesting for us, and we started working towards building the HBase and Phoenix cluster. So we run our operations in AWS. We currently have an EMR-based HBase cluster running version 1.3 and Phoenix 4.11. For load balancing purpose and hot failover, we run a primary and a mirror HBase cluster. And for folks who run their operations in AWS or in cloud, relevant for them, we run these clusters in different availability zones, basically from a durability point of view. So in case one of the availability zones is down for a significant point of time, we don't have any impact on our operational side. Our data pipeline is fairly straightforward. We have a Spark-based computational cluster, which runs a bunch of these algorithms and stages data to HDFS. And we ingest this stage data in HDFS to HBase using incremental bulk loads. Here is a quick look at the architecture. All right. So we have the import cluster where data is staged in CSV format. And we have HDFS and Eon services running on this cluster. On a day-to-day basis, during off-peak hours, we run import jobs, which loads the CSV files and converts them into H files. These H files are transferred to the live cluster and the mirror cluster. In addition to that, we also transfer the H files to S3 buckets for durability and disaster recovery purpose. In case we ever want to recreate a new HBase cluster, we go back to the backups in S3. This job currently runs a couple of times during the off-peak hours and has a throughput of 3 billion rows per day. Access to HBase and Phoenix cluster is through the Phoenix thin client, which is embedded into the PQS cluster. PQS is the Phoenix query cluster. Basically, PQS allows access to HBase and Phoenix for non-Java clients. For that purpose, on the API host, we have PhoenixDB, which is a Python-based DB implementation that manages the interaction to HBase via PQS. Our HBase cluster is made up of 60 region servers with 4 CPUs and 8 CPUs and 60 gigs of RAM. It has 30 gigs of HBase allocated to the region servers. It has 12 terabytes of hard disk and enhanced networking enabled. This is something specific to AWS instances. PQS instances are running on one of the newest compute optimized instances available in AWS, C5-4X large with 16 CPUs and 32 gigs of RAM. These are EBS only instances. Basically, it's a disk is attached to a network. And these instances also have enhanced networking enabled. So the first use case we're going to talk about is the IBD. IBD is identical by descent. It is a patented algorithm by 23andMe that helps find relatives in a database by doing pairwise DNA comparisons. Running this algorithm allows us to find stretches in DNA that are common across customers. And if there's a continuous region within the DNA that is shared by individuals, it is likely to have been inherited from the same ancestor. That is, they are related. We also have some conditions within the algorithm to make sure we filter out any regions that could have been detected just by chance. So here is a quick example. So humans have 23 pairs of chromosomes. The highlighted region is a small area within the DNA that is common between person 1 and person 2. That is an area we are interested in. This information internally, it's called a shared segment, and that information gets stored in HBase. So more the number of segments, larger the segments, stronger the relationship. So how does IBD work? We process thousands of customers per day. Each customer has millions of genotypic locations. For every customer, we do a pairwise comparison across the existing database, which is 5 million customers. So there are effectively trillions of these comparisons happening on a day-to-day basis. And the segments that I showed earlier, those kind of segments are saved to HDFS and ingested into HBase. So this is the Phoenix schema. The two main entities for IBD are segment and relation. As I said earlier, segment is the small region within the DNA that is shared by a couple of individuals. Individuals can share a number of segments across the DNA. All of this information gets rolled into a single row, aggregated into a single row with that defines a relationship. So we store that information in a different table called relation. So the most important design criteria when creating a Phoenix table is the primary key and the order of columns in your primary key. Mainly because when you have the columns in your filter, those are the columns you want to have in your primary key, because that will ensure you don't do full table scans and use something like range scans or skip scan that is basically beneficial for performance. So here are some of the Phoenix optimizations we have in our tables. Fast diff block encoding. So in HBase, there is a lot of metadata information that is duplicated across multiple cells. Fast diff encoding basically optimizes that, removes most of the duplication. It improves your, it optimizes your disk usage, improves your read throughput, overall better performance. In addition to that, data blocks are compressed using GC, again, to optimize disk I/O. Row-level Bloom filters are helpful when you're looking for specific gets. Bloom filter is nothing but a in-memory index that gives the probability of finding a specific row key in a given store file. It does not have any false negatives, but there is a possibility for false positives. We use salted tables, but this is something use case specific. It's especially useful if you run into region hotspotting. Salting your tables will ensure that the scans are performed in parallel across all your region servers. In addition to that, something to be conscious about is to avoid full table scans, especially at scale of your Phoenix tables. So range scan and skip scan perform at have much better performance, and that's where the design of the row key comes into picture. In addition to that, all conditions on the non-key columns get pushed down to these region servers. So predicate pushdown helps decreasing the number of rows that get shipped to the client. If you're doing any client side, for instance, if you're doing merge sort join, which is done on the client side, applying the filter on the region server optimizes the amount of data that gets shipped to the client. So here is an example. So the two tables, the relation table and segment table, together they have over 1 trillion rows. And there are a wide variety of queries that we hit these tables from Phoenix. Like there are joins, aggregations, filtering, bunch of different things. And the performance of all these queries on an average has been less than 100 milliseconds. So here is an example. So for customers of 23andMe, you can log into the website or the app and look at your close relatives based on the DNA comparisons that we have done. So it's a quick snapshot of how it looks on the website. It gives a list of all the individuals in the database that you're related to, and the strength of the relationship. On Phoenix side, the query translates to something like this. So for a given person, based on a condition, half is basically referring to something called centimorgan, which is a unit of measure for measuring genetic distance. So we want longer the segment, stronger the relationship. So these conditions will ensure only close relatives are returned. So it translates to a query like this. And before deploying anything, it's important to look at the explain plan. So few interesting things about the explain plan here from Phoenix. First thing, it is a 60-way parallel scan. So these tables are salted, and we have 60 region servers. So the scans are running in parallel across all the region servers. Range scan is done because person ID is the leading key of the primary key, and we are filtering on that particular column. It does a scan of all the keys for that particular person ID 1. And finally, server-side predicate pushed on the centimorgan length that is applied over here. This is the second interesting report that basically shows the segments that an individual shares with a couple of his relatives. So the query translates to something like this for a given customer ID and couple of relatives for that particular individual and a condition on the centimorgan value. It returns all the segments associated that are shared between these individuals and ordered by the chromosome and the starting location of that particular segment. So interesting thing over here is compared to the previous query, it does a skip scan over here instead of the range scan. Skip scan performs better than range scan. In skip scan, Phoenix identifies the list of key ranges that can be filtered on, and that is a subset of the much bigger key range if you just filter it based on person ID 1. In addition to that, the server-side filtering is done on chromosome and start, and finally a merge sort on the client side before shipping the results back to the endpoint. So here is another example, relatives in common. So this report helps return all the relatives that I share that are common between myself and another close relative of mine. So right side, you see the report with all the common relatives that a sample person shares with someone called Greg Mendel, and some additional information about the strength of relationship and stuff. The thing about this query that is different is that it involves a join, and each of these tables actually have billions of, well, it's actually self-joined. This table has billions of rows in it. So the first server-side filter is applied on the person ID 1 for alias R1, and similarly on the alias R2, it's applied on the person ID 1, which is the relatives ID, and we do a join on all the relatives that are common, that returns the common individuals for these two people, which are person ID 1 and person ID 2. So if you look at the explain plan, we talked about the range scan and the server filter. What's interesting over here is the parallel inner join. This is Phoenix by default does hash table joins. As part of the hash table join, it ships the results from the right hand side of the query to all the region servers, and the join is done and the join is done on the region servers. In some of the databases, it's also called broadcast join. Marcell will be talking in detail about the technical details of how the hash joins work and what performance fixes that we have implemented. So this is another use case. Ancestry composition is something we have recently released. This allows for analyzing someone's ancestry based on the DNA. This report shows the percentage of your DNA across 31 different populations, and it is purely generated from using Phoenix queries. I already touched upon the segments and relations datasets. In addition to that, I mentioned that we also store the responses received from customers as from the service. We combine all three datasets to generate the ancestry composition report. So on the left side, you see the ancestry composition report, where is for some sample individual, 47% of his ancestry is from European, and there are some subpopulations that goes into much further details of where this ancestry is from. On the right side is the Phoenix query, and as you can see, it's actually fairly involved and complex query that brings together 3 different tables with over trillion rows. And when we ran a variation of this query for the first time, it took about 8 seconds to run, and we started analyzing to understand the bottlenecks and improve the performance of this query. So one interesting characteristic of this query is that the blue rectangles does not change between individuals. So for any customer, the predicates pushed on over here are same. So we looked into how we can use this characteristic and improve the performance of hash joins. And to go into those details, I invite Marcell.
Hello? Okay, cool. So, since this is a data conference, this is going to be a little bit of a review for everyone in this room, but let's go over just what a join is very quickly. You have 2 tables here. Blue is people with the eye color IDs, and then the yellow table is the actual values for the eye color. So as we all know, when you join them, you just combine 2 tables into 1 table. So now we have the nice human-readable values there. A hash join is an implementation of a join. So you take this yellow table back here, you turn it into the hash table you see next to the blue table, and as you go down the rows, you use the eye color ID as the key to the hash table. So this is pretty cool because, as we know, hash tables are O sub 1 for lookup, and so we get an O sub n algorithm for the join, where n is the number of rows in the blue table. So let's talk about how we do this in Phoenix, which is a little bit more complicated because it's a distributed system. Does anyone here know how Phoenix does hash joins, out of curiosity? Oh, cool, great. So you have a client and then some number of region servers. And here we have an example query, which is going to be the same thing before we select the people, join in the eye color. So step 1 is going to be to build the hash table that we saw previously. So take the yellow table, which is the eye colors, and turn it into a hash table. So for this, the Phoenix client makes a query to all 3 region servers. And it says, give me all the values in the yellow table. It gets it back, and it builds this hash table that we see this little bright yellow thing is the hash table. So that says, color 1 is red, color 2 is green, etc. Then the client will distribute the hash table to all the region servers. So basically, that RPC call that transfers the 1 megabyte or whatever, 10 megabytes of data over to region servers. And then the next step is we execute the join algorithm that we saw before with the red arrow, where we go down the rows of the blue table one by one and do a lookup in the yellow hash table to get the joining value. So that's step 3. Then we return the values. So step 4 then is going to be to release the hash join tables and then return the results to the client. So the little X there shows that we're kind of freeing the memory, run garbage collection, whatever. So that's kind of how it works in Phoenix. And here's a timing breakdown of the execution. So the bars are not really representative since it depends on the data, but basically you have a phase 1, which is to kind of generate the hash join table, which breaks down into kind of 2 components. Step 1 is compute or IO bound typically, which will read the data through a range scan. And then step 2 will be kind of network bound typically. So you'll actually, from one client, transfer, let's say 10 megabytes to 60 region servers, get 600 megabytes of transfer, which will be typically network bound. And then the blue part is the phase 2, where we do the execution of the join algorithm. So step 3 takes most of the time here. It'll be typically compute or IO bound, where you iterate down the rows of what we call the driving table, which is the table that kind of drives the join, and then you look up in the hash table for your values. So that'll take up most of the time in phase 2. Also, releasing the data, returning the results might take like a few milliseconds. So that's the timing breakdown. So some quick pros and cons. Hash joins are pretty cool because they're really fast. As I mentioned, it's O sub n on number of rows. But the bad things are, number 1 is that you have to broadcast the hash table to every single region server, which can be quite slow for large hash tables. Typically, Phoenix kind of recommends to keep these below 100 megs in size. And also, we rerun the generation of the hash join table for every single query. So you see here as an kind of an example, we have select start from person, where person.some value is in select some value from large expensive table. And so this is, it's using in here, but Phoenix does a join here. It's basically a left join with null or something. And then we have person ID equals 1, 2, 3. So an observant person might look at this and say, hey, look, only this thing is going to change across queries, whereas this is constant across all the queries. So let's look at the performance breakdown of this query. So here we have our 3 region servers, and each of these kind of bar thingies represents one query. So the orange part corresponds to the orange part of the query, which is executed for every single query. So we have one query here that takes this much for the orange, which is kind of like the subquery to generate the hash table. And then the phase 2 takes this much time because maybe it's a smaller table for the blue table. And so we have a capacity for whatever width of the slide is of 5 queries per width of slide, which is like a minute or something, or a second. So what if we can do something better, though? In particular, what if we can look at this query and say, hey, we don't want to make this expensive query every single time because it's going to be the same across queries. Now, as we all know from computer science, you can do caching in this case, but you can't do application level caching because this ID changes. So if you try to cache in the API server that's doing the call, you'll basically it'll be useless because every person ID will change and you can't use your cache results. But if we dig into the internals of Phoenix, we can cache these results. So we have a new hint, which is here in yellow. It's called use persistent cache. So you put this into the query over here, and this will tell Phoenix, hey, Phoenix, some of these things are going to be useful for further queries later on. In particular, it will take each query statement, so to select a value from large expensive table, it'll take the kind of the normalized string of that query, do an MD5 hash or SHA hash or whatever, and use that as a cache key or an identifier. It'll say, hey, I'm going to keep this around, and maybe I'll need it later. So on the first execution, you do both phases, phase 1 and phase 2, where you generate the hash table with the query on large expensive table, and then you scan and execute the join. So it's O sub large expensive table plus O sub person. But on second execution, you now have just O sub person. So you kind of lose half of the phases, which might be half or more than half the time, depending on the relative sizes. So back here, we had, again, 5 queries per width of slide. But if we put in the hint, all the orange will go away after the cache has been warmed up once, frees up all the space, and we now have, I don't know, like 10 queries per width of slide, so a lot more. And the improvement really depends on the relative nature of the cacheable part versus the driving table. And at 23andMe, basically we have a lot of genotypic data, which is used in queries, and it's kind of uniform across all the queries. So for us, it's a huge benefit for a lot of queries. For our CEO, for our countries of ancestry query, we have saw a speed up of basically 3 seconds for kind of the first query that warms the cache, and then goes on to 1 second once the cache is being used. And if for our new query we're developing, which is around your DNA family, it goes from 30 seconds, basically unusable in production, to less than a second, just because of the nature of how our tables are set up. So it's been a big improvement for us, and we're kind of rolling it out in production basically now. Let's see. Oh, a new config for this is max server cache persistence time to live milliseconds. Basically, how long we should keep around the persistent subquery cache. So 10 minutes a day, whatever your use case might be. And some future work. Some future work that we might add later on to this is hinting. So for example, you might have some knowledge about when you want to expire things, maybe like the time of day or a certain day. So you might add that as a suffix to the hash of as a suffix to the cache key to say, hey, I want to evict this now or warm it for tomorrow. Also, one thing we're running into is handling really big caches. For example, like 1 gigabyte or even 10 gigabyte caches is something that we're trying to figure out. Typically, Phoenix recommends you put the smaller data on the left-hand side, on the non-hash table side, so you won't see this in normal phase, but we're flipping the equation to take advantage of the caching. And so we're seeing these giant kind of subquery caches for hash joins that are inefficient. So some ideas are off-heap cache, using memcache or Redis or something, but it's kind of hand-wavy for now. But yeah, this is helping us a lot, and it'll be rolling out in, I think, the next version of Phoenix, so 4.15 or whatever it is. And yeah, back to Tulasi. Oh, yeah, sure, yeah. Yeah. Oh, there's a microphone there, I think, if you want to. Oh, yeah, whatever. Yeah.
Can you explain this caching part a little bit more? Is that always an off-peak cache or?
Oh, yeah, sure.
I'm kind of confused whether I'm configuring an off-peak cache for this, or is it always going to be an on-peak cache?
Yeah, sure. So what? So the way. Let me just go back to the slides real quick. So this yellow thing is basically the hash table is used for the join, and this will be sent to all the region servers, and it's stored in the Apache coprocessor memory, and in the subquery cache that we're introducing here, it will be stored in the Apache coprocessor memory space in the heap. Does that answer your question? Oh, that's like an idea for the future potentially. So because you don't want to keep maybe like 100 gigs in heap or something like that. So you might store that in somewhere else.
Thank you.
Yeah. Oh, yeah, sure.
Are the cache tables then duplicated across all of the region servers for the duration that they live in the cache?
Yeah, so yeah, every region server has the exact same hash table for the duration of the query. And then with this cache, it'll be kept around beyond the duration of the query.
My question is the cache identical across all of the region servers, or is it kind of?
Yeah, it's identical because you don't know what data might be on every region server. So yeah, but that'll be an optimization to make it not be the case. Where were we? Cool.
Cool. Thanks, Marcell. So here are some of the, there are a number of properties that we need to tune when we are running the HBase Phoenix cluster. Here are some of the properties for reference purpose. So one of the things that we had to tune was the data node max exivers. This is related to the number of open connections that are allowed on the data node side. So the default value is too low, and we are currently running it on 4096. It depends on your workload. You need to run some trials and tune it to a value that works for you. In addition to that, we've also enabled short circuit reads. Basically, what it does is it allows HBase to do reads directly from the disk for the files that are present locally instead of having to go via the data node APIs. Again, to improving the performance and read throughput. We also have the stale data node property enabled to make sure data present on data nodes with any health issues are not used for processing. On Phoenix side, we have some properties that we have configured, things like setting up the queue size to allow for higher throughput, set up the time to live of the server-side cache. This property is specific to the non-positioned cache that we just talked about. This cache is visible only for the duration of the query that it is running. So if your queries are typically running less than a minute or less than a few seconds, this value can be much smaller. In addition to that, disable the row key order. This ensures that Phoenix doesn't sort the row keys before shipping the results back to the client. This again, use case based. We didn't have any need for that happening, so that has been disabled. And server-side cache bytes is the maximum size of the hash table that can be saved on the heap space of the region server. And this is again related to the hash table joins. On HBase properties, major compactions, the default major compaction process is disabled. We run it on demand. And since we have the live and mirror clusters running, we balance the load across these clusters. Because during major compactions, a lot of resources are used by HBase. Set up the zookeeper timeout because this is the duration it takes for master to detect if a region server is down. This is something again specific to the user cases. In addition to that, set up the number of region server handler counts. That is a factor of the number of cores you have on the cluster. And optimize the memstore flush size depending on how frequently you write, or if you're more of a read-heavy application. There are a couple of OS settings that are standard in pretty much any HBase installation. There's a lot of online documentation around that, which is to disable the transparent huge pages and the swappiness. So through experience, we've realized that there are a number of properties in Phoenix that affect the query timeouts. So these are those things, and it is spread across Phoenix, HBase client, and also the region server. And we were able to deterministically tell how long a query will run or how long a client will wait for a query to return before timing out. So some of the lessons learned in production. For folks, if you're running in AWS, using enhanced networking is a big help. A lot of times, for network issues, the error propagates as a socket timeout or a timeout kind of an error. Very tricky to debug. Having enhanced networking gives you high network throughput and definitely helps with performance. If you're using PQS and running in AWS, it's important to have your PQS cluster running in the same availability zone as the region servers. This guarantees very consistent performance of queries over a period of time. And this is something we've encountered recently with respect to statistics collection in Phoenix. For some reason, we detected that when statistics is enabled, we are seeing duplicate rows written by Phoenix. And it was also having a negative impact on the query performance. This is something we are still investigating to better understand what is causing this one. But this is there for reference purpose if anyone else is facing similar issues. Last but not least, monitoring. There are a number of metrics that are available in HBase. And having a good solid monitoring system will help you understand what are the bottlenecks in your cluster, tune it over a period of time. We've developed in-house custom plugins and using New Relic, and we use that for our monitoring. Here are a couple of tickets. One is Phoenix 4666. This is the subquery caching functionality that Marcell just talked about. In addition to that, we're also working on providing client-side hash aggregation, which is helpful for client-side sort merge joins. All right, we have few minutes for Q&A. Sure. So PQS is the Phoenix query server. It allows for having. Just a minute. So PQS cluster is basically hosts the Phoenix thin client, and it allows for accessing Phoenix through non-Java clients. So we have a PhoenixDB implementation. It is also open source, and this is installed on the API host through which we make connections to the PQS course, and that is responsible for connecting to Phoenix and HBase. It implements the Avatica protocol, and it's a wrapper around the JDBC driver. Yeah, the queries will be triggered against the PQS cluster, which interacts with Phoenix servers on the region servers. Yeah, that's a good question. So for PQS, we use a simple random selection of nodes. We're currently exploring elastic load balancer using in AWS. So the way it works is between the communication between PhoenixDB and PQS is that there are a number of HTTP calls that happen for every query, and it's important that all of those HTTP requests have the same connection ID, and it's important that when building the load balancer, it's important that all the HTTP requests associated with that connection ID go to the same server, and that can be enabled through sticky sessions, and yeah, there are some features available in AWS to do that. Right, random selection of from the given PQS source. Yeah, sure. So the question was around how do you balance load balance traffic to PQS cluster? Yeah, good. So we run in a private VPC in AWS. Yeah, the HDFS level replication is default value, which is 3, and as far as H files itself, we ship them both to the live cluster and the mirror cluster. They're generated by the import cluster, and we use DCP to send them to both HBase clusters, and from there they are ingested using incremental bulk load. Yeah. So we don't do manual region splitting. We do major compactions on a weekly basis, and we balance it by making sure the traffic is shaped balanced between the two clusters that we have. And when major compactions is running, obviously that cluster has very few resources available for serving the product queries itself. So we have automated feature switches available on the product side, which can control the amount of traffic going to each of these clusters. So when the major compaction is running or some administrative activity is running on one of the clusters, we make sure that cluster has much smaller traffic. Yeah. We use a small multiple of number of region servers available. It doesn't have to be equal, because over a period of time you tend to add more nodes to your cluster, so it's better to have a multiple of that. Yeah. Yeah, good. Sorry, could you repeat that question? Yeah. So recently, Phoenix started work towards publishing metrics at Phoenix level itself. So there are metrics available both at JVM level and even at the connection level. But as far as I know, they're not yet released into the code base itself. But I know there's work going on there. And I think it will be great once that is merged. It will enable us to build our own tools around it for monitoring purpose. Sorry, you had a question. So the number of regions is depending on the number of the size of the table itself, and it's specific to the table. We have a few hundreds of regions per table. It is a EC2 instance running in AWS. All right, yeah. We have considered, but we haven't actually got a state where we are ready to deploy it in any way. I mean, we're a fairly small team, and we've been running operations using HBase and Phoenix for 3 to 4 years now. I would account for at least 15 to 20% on the operational side. All right, yeah. Mechanisms developed. Yeah. Good.
The question is, how does the subquery cache get distributed? Right now, it's just a broadcast from a single node. But you're right that for large caches, it would be good to have a better fan out or something, anything but broadcast.
Cool. If you have any questions, feel free to talk to me or Marcell offline. That's all we have for today. Thank you very much.